Institute of Engineering and Technology.
Hello students, in this talk we are going to discuss about a very different type of convergence which is observed in case of alternating series. It is known as absolute convergence. We have seen convergence and divergence. We have also seen its test, some particular series like geometric series, P series, harmonic series, telescoping series. We also gone through some fundamental tests like nth term divergence test. What do we mean by integral test, and what do we mean by comparison test? But today we are going to discuss about a special type of test which is known as a ratio test. This test and this convergence, they are very much interesting as well as beautiful also. The reason why we are considering this type of convergence is it will not happen every time that our series is with positive terms. It may happen that our series is changing its sign term by term. So in such cases, we need to go for a different approach, or we need to consider an approach which will help you to identify its convergence still if our terms are negative. So let us start our first part, which will give you idea about absolute convergence. We'll see what do we mean by absolute convergence graphically. How many different possibilities are there for convergence, in which scenario we cannot test our convergence absolutely. Later on we'll see our ratio test, which is depending upon only two terms of the given series. So let us start our first part, which is infinite series. In infinite series, I want to first of all cover absolute convergence. So in absolute convergence, the definition is something like this: a series summation an, it converges absolutely if it is with help of its corresponding absolute values in series summation mode of an is convergent. This simply means that if you want to check summation an is convergent or not, we need to consider our regular series, but now the input of terms are with absolute value. We can say that if this series of magnitude of an means the value which is absolute value of the series, if that series is convergent, our regular series is also convergent. But the converse is not true. It may happen that our regular series is convergent, but its absolute series is not convergent. We'll see through examples. So for that, we need to understand this new type of convergence or absolute convergence graphically. First case is, what do we mean by divergence if my series is alternating series? Alternating series means a series with fluctuation in sign. So here I am defining one such series with help of minus 1 raised to n into n. We can see very clearly that the term by term my value of input, which is an, is moving from positive y-axis to negative y-axis. Like initially my value of n is 1, so it is minus 1 raised to 1 into 1, so it is minus 1, so it is below x-axis. Then after n is equal to 2, so it is minus 1 raised to 2 into 1 into 2, so it is plus 2, so it is above x-axis, and so on. It will keep on fluctuating its value. Now how to check whether this series is convergent or not? It is quite difficult for us to consider whether this is convergent or not directly. The reason is, it may happen that the negative values are cancelling positive values, and so for the remaining residual values, we don't know what will happen in future or what will happen at infinity. So to understand this thing in a present frame, let us consider magnitude of an. Now if I focus on this part only, which is a negative part, so I am considering negative values of the function with red color and positive values with blue color. But then once you take the magnitude of the input, that red bars are also reflected towards the positive. And that means now in place of considering all those red bars, I am neglecting all those red bars and then I am focusing only on this blue bars. If this new series of blue bars is convergent, then I can say that the alternating series minus 1 raised to n into n is convergent absolutely. So see, it is not regular convergence, it is convergence with condition of absolute values, so it is absolute convergence. In this case you can see dramatically values are moving towards infinity, and so this series is divergent. So it is not absolutely convergent. Now let me take another scenario. Here I am taking a series which is eventually decreasing, but it is alternating also by nature. So again see, the bars are fluctuating towards x-axis. Some bars are above x-axis and then some bars are below x-axis. But once you move towards infinity, the values are decreasing. So now how to check whether this series is convergent or not? Again I am taking the same scenario. I am reflecting all negative bars towards the positive value and then I am creating a new series. So here again you can see the values are decreasing, and now by taking magnitude of minus 1 raised to n into 1 by n, value is 1 by n. This simply means that this is represented by harmonic series, which is again a divergent series. But in same case, suppose I consider 1 upon n square. In that case it will happen that the series is decreasing towards 0 and it is convergent also, being p series with p equal to 2 which is greater than 1. So keep in your mind these two pictures. The first picture was alternating bars, and then in second picture I reflected all bars on the upper side and represented all lower bars with red color. So see, if you look carefully, we are always interested in the positive values of the term only. It may happen that your series is alternating, so in that case we cannot check any convergence directly, but we can check its conditional convergence. Now let us go for a test for which I was talking about in the initial part of this video, which was ratio test. Now let us define first of all the ratio test. So the theorem is something like this. For any series, it can be positive, it can be alternating by nature. Summation n from 1 to infinity a n. If this limit n tends to infinity, a n plus 1 upon a n, if this in magnitude is resulting into a value k, and if k is less than 1, then this series is absolute convergence. If this k is greater than 1 or it is tending to infinity, then it is divergent. And if k equal to 1, then this test fails. Now let us look inside this first condition. What do we mean by value of k is less than 1? If value of k is less than 1, and if I consider the condition for this ratio test, which is limit n tends to infinity, magnitude of a n plus 1 upon a n equal to k, I can separate those magnitudes. So it is mod of a n plus 1 equal to k times mod of a n at n tending to infinity. That means I am talking about two consecutive terms happening at infinite stage of the given series. I am not talking about at any finite stage. I am checking what is happening at infinity. Because if at infinity your values are reducing to 0, ultimately you can say your series is convergent. So I am not interested in any in-between finite stage of the series. I am interested right now only and only at what is happening at infinity. So if at infinity your two consecutive terms are holding this ratio k and that k is less than 1, in that case it will happen a n plus 1 is less than a n. So what does it mean? It means that a n, which is a current value, is bigger than the upcoming value, which is a n plus 1. So that means a n is bigger value and a n plus 1 is comparatively lower value. So step by step your values are reducing. Once you know this structure of the series, that term by term values are reducing at infinity, ultimately at some time it will happen that it will eventually become 0. And that led us towards that nth term test, that if nth term of any series is 0, it is decreasing, it is continuous, obviously it is going to be convergent. As here I am taking a mode of this, it is absolute convergence also. Now let us check another case. So what will happen if k is greater than 1? This simply means that an plus 1 is greater than an. That means the upcoming term is comparatively bigger. So obviously at infinity, if this is happening, that means term by term your values are increasing, and so it will move towards infinity, and hence your series is divergent. What will happen if k equal to 1? This means that after infinitely many terms, your series is coming into the equilibrium. That means in a stable mode, an plus 1 is equal to an. So there is no change, they are moving parallel to each other. In such cases, we cannot say anything. It may happen that after reaching 0, they are moving parallel to each other. It may happen that they are moving parallel to each other after reaching some non-zero number. We don't have any surety for that, and that means this test is failed if that ratio is equal to 1. Let us check this thing graphically. If I consider the first case, that is summation n equal to 1 to infinity an, that is converging absolutely using ratio test. If that ratio k is less than 1, you can see clearly term by term my bar height is reducing. And so to represent that ratio, I am connecting that bar with y-axis with help of that black line. So if that ratio is decreasing, you can see clearly in the first bar, the first rectangle is comparatively bigger, and then onwards the height of the rectangle is reducing. So gap in between two values is reducing, and that indicates the convergence. Now let us take second case. If value of k is greater than 1 or it is tending to infinity, our series is divergent. Now here you can see the gap in between those two black lines is constantly increasing, or ultimately it is not moving towards 0. The gap in between two terms is constantly increasing, and that simply means that term by term my value is increasing, and so ultimately it will move towards infinity. So this is whole idea about convergence and divergence of series using ratio test. So remember, the bottom line is, if the upcoming term is decreasing, means if it is less than the current term, if an is greater than an plus 1, your series is going to be convergent. If an is less than an plus 1, your series is going to be divergent. Now let me take third and the last case, which is k equal to 1. Now this is not happening exactly at the initial stage. This is happening at infinity. At infinity, all my terms are remaining at the same height. That means that ratio is now equal to 1. So that means I cannot conclude anything. If exactly this scenario is over there, that indicates that after infinitely many terms of consideration in series, still there is some height which is remaining to add into the answer, and that gives you that it is moving towards infinity. But suppose the same thing is happening on x-axis, means the height of this bar is 0, means now points are lying on x-axis. In that case we can say it is convergent, but it is very difficult to check exactly which of these two conditions is satisfied. So in general we are saying that if k equal to 1, then ratio test will fail. Now let us consider one example of this ratio test. If I take n from 1 to infinity 2n factorial upon n factorial into n factorial, it is very difficult to check convergence for this kind of factorial series. So for that we need to go for the ratio test. So I am assuming that this series is denoted by an. So for that reason, my two consecutive terms an plus 1 and an are in ratio given by this value, 2 times n plus 1 factorial upon n plus 1 factorial into n plus 1 factorial. Everywhere I am replacing n with n plus 1, and in denominator I am taking an. So it is 2n factorial, n factorial, n factorial. Now after simplifying this, in denominator I am expanding n plus 1 factorial into n plus 1 into n factorial. In numerator I am multiplying 2 inside this factorial. So I can cancel out all these n factorial terms, which gives me ultimately 2n factorial in numerator and 2n factorial in denominator. Cancelling that 2, ultimately will result into this thing. And so as we are considering n tending to infinity, I need to take that n outside the calculation of numerator and denominator. So which gives me answer 4. And this means that the series is divergent. Now look carefully how it is divergent. Ratio of a n plus 1 upon a n is resulting into 4 at n tending to infinity. That means at infinite stage also a n plus 1 is equal to 4 times a n. So a n plus 1 is 4 times bigger than a n at infinity. So this simply means that a n plus 1 is still increasing after infinity also, and so ultimately it will reach to infinity. So this is beauty of this test. If you look carefully, we derived 3 tests for convergence. The first was nth term divergence test. Secondly, we have seen integral test. In integral test, you need to define a function satisfying certain conditions depending on a n, and then you need to integrate it, and there are some limitations. Secondly, we defined comparison test. In comparison test, on given series a n, you are defining new series b n to compare, and that is also comparatively difficult to check whether given series b n will be in our control or not, or whether we can find the dominating term in the given series or not. Whereas in this case, in ratio test, you are not moving outside the given series, you are remaining inside the series, you are identifying 2 consecutive terms, and hence you are concluding your result. So this test is comparatively easy. So I hope all of you understand this test, which is ratio test, and all of you are now familiar with the idea of alternating series and idea of absolute convergence. Later on, we are going to define conditional convergence, root test, and a limiting case of ratio test, which is Rabbit's test. Thank you.
LJ Institute of Engineering and Technology.